Imagine you are riding a roller coaster. This is the force that keeps train from falling off the track. It is a constant first introduced by Lagrange in classical mechanics and acts like the force applied by the constraints on the system. In this video, I will start from the basics and show you step by step how and why this constant appears in machine learning models to compensate for a low number of observations. In other words, to help us when our data spreadsheet does not have enough rows. Along the way, I will discuss concepts like penalty term, regularization, ridge regression, lasso regression, overfitting, bias, variance, and the bias-variance trade-off. After covering all the concepts, at the very end of the video, I will show the implementation of these concepts in Python programming language. Since this video is part of a playlist on machine learning, and to keep this video self-contained, let me quickly summarize the key concepts that we need for the rest of this video. If you have watched the previous videos of the series and remember the details, you can skip to the next chapter. In this video, we discussed that a data spreadsheet is governed by a probability P, which is a function of the columns of the spreadsheet, which are the variables of the system. It tells us the chance of the occurrence of a given row of the spreadsheet. We also discussed that the true form of P is never known. The probability is in general a function of time. But due to the maximum entropy principle, evolves toward a static form that we call the equilibrium state and becomes static. In that state, the system fluctuates around the minimum of this F in the probability function, which we call the effective free energy of the system. Since the system fluctuates around the minimum of effective free energy, we can neglect the higher order terms in its Taylor series, and that provides an estimation for the probability function. We show the estimated probability with G to distinguish it from the true probability that we refer to with P. In this video, we showed that after rearranging the terms in the Taylor series, we can write the probability distribution in the following form, which happens to be the Gaussian distribution for Y. Here we have shown the target variable, the column of the spreadsheet that we would like to predict by Y, and the rest of the columns of the spreadsheet, the predictor variables with x1, x2, etc. We know that in a Gaussian distribution, these terms in the parentheses are just equal to the mean of the target variable Y. And this equation is what we call linear regression in machine learning. At this point, the problem is to estimate some values for the remaining constants of the Taylor series of F in the probability distribution G. For that purpose, in this video, we use the concept of relative entropy, which was first introduced by Ludwig Boltzmann in physics and reintroduced in statistics a century later by Kullback and Leibler, where it is known as the Kullback-Leibler divergence. This relative entropy is a measure of the information we lose if we use the estimated probability G in place of the true probability P. We discussed that if we have a fairly large number of rows in our spreadsheet, we can use the law of large numbers to replace the true distribution by its empirical estimate to turn this relative entropy into a practical tool. At this point, our goal was to minimize this relative entropy, which in turn means minimizing the information loss. We showed that after a few straightforward steps, this becomes equivalent to maximizing the logarithm of an object called likelihood. We discussed that the likelihood is defined as the multiplication of the estimated probabilities of each row of the spreadsheet. Therefore, our task was to find a set of beta parameters, the constants of linear regression, that maximize the logarithm of likelihood. Done with summarizing previous videos. Let's now get into the subject of this video. As I just explained, we use the law of large numbers to replace the true probability distribution in the relative entropy with its empirical estimation. By that, we assume that our data spreadsheet had too many rows. In other words, our sample size must be very large for the maximum likelihood method to work properly. But what if I have a low number of rows in my spreadsheet? The short answer is that we cannot estimate all the parameters together. Let me explain. If the parameter space is a jigsaw puzzle, every row in our spreadsheet can only uncover one of the pieces. But we have a degree of freedom to choose which location on the game board we would like to figure out using that row of data. If we have too many rows in the spreadsheet, the entire puzzle can be solved. If we have a limited data, we can figure out a smaller area. Getting back to machine learning, when we have a small data set, we must reduce the number of unknown parameters in our estimation of probability distribution. The brute force solution would be to simply collect more data, but sometimes collecting more data is very expensive and not wise. Another approach is to reduce the number of columns in our spreadsheet, because in, for example, linear regression, we have one unknown parameter for each column of the spreadsheet. If we have a good knowledge of our system, we can decide which columns are less important in predicting the target variable and just eliminate them. Another way of reducing the number of predictor variables, the features, is to merge them into a new column. For example, in this video, I explained that in one of our projects, we had recorded the activity of a high number of neurons in the brain. Then, inspired by magnetic moments in physics, we summed all the cells in each row of the spreadsheet to engineer a new feature similar to the magnetization in physics, therefore reducing the number of columns to just one. So far, I discussed system-specific methods. For example, summing over all the columns of the spreadsheet to create a new column probably won't lead to a meaningful new feature in most situations. And that leads us to the subject of this video, to find a systematic way of solving small data size problems. In this video, I discussed that when throwing a coin, in principle, we can measure all the forces applied to the coin by our hand and air resistance and gravity to predict exactly if we end up with a head or a tail. But in practice, to avoid measuring all these factors, we can explain the event using probability distribution. In other words, we can cover our ignorance by a probability description of the event. We are now going to use the same concept. Since we don't have enough data to uncover all the unknown parameters of our machine learning model, we describe the unknown parameters of the model by probability distributions. For example, we can say that due to the low sample size, I cannot determine beta 1 with certainty. Instead, I will assign a probability for every value it can take. Let's, for example, assume a Gaussian distribution for it. By this, we assume that beta 1 equal to 0 has the highest chance, but non-zero values are also possible, but with less chance. Now we move on and assign the same probability distribution to other unknown parameters of the model. Remember that we use the max entropy principle to write the chance of occurrence of a specific row in our data spreadsheet by ignoring the higher order terms in the Taylor series of effective free energy. That was for when the beta parameters could be determined with certainty. Now that the beta parameters are being described by a probability distribution, the chance of occurrence of an event, a row in the spreadsheet, is what we had before multiplied by the probabilities of the beta parameters. To understand why I am multiplying the probabilities, imagine I throw a coin and a dice. What is the chance that I get a head for the coin and number 6 for the dice? Since the two are independent of each other, it would be half, which is the probability of the coin, times 1/6, which is the probability of the dice. Now that our estimated probability distribution is updated, we need to recalculate the information loss minimization process. In this video, I discussed that information loss is described by relative entropy, known as Kullback-Leibler divergence in statistics. We also discussed that after a few straightforward steps, we end up maximizing the logarithm of what we call likelihood in statistics, which is defined as the multiplication of the chance of each row of a spreadsheet. Let's now insert our parametric form for the chances, and now rearrange the logarithms. The terms that are not a function of the beta parameters are just constants shifting the whole function up or down, but they don't relocate the position of the maximum in the parameter space. That means we can drop them out, and it won't change the solution to the maximization task. Using the same argument, I can multiply the whole argument by the negative of 2 times the variance, and that turns the maximization task into a minimization task. The reason is that the negative sign will flip the function so that what was maximum becomes a minimum. The first term is just the residual sum of squares, which, as we explained in this video, is the sum over the distances between the two y values in our spreadsheet and the line of the linear regression. In machine learning, the second term is referred to as the penalty or regularization term. In physics, this term was first introduced in the 18th century by Lagrange in classical mechanics to explain the motion of objects constrained to move along a specific path. Just like in a roller coaster, where the train has to move along the track due to the forces that the track applies to the train. The lambda in this equation represents those track forces applied to the wheels of the train. In machine learning, this lambda is called a hyperparameter, since it is a parameter that tunes the unknown parameters of our model. Inspired by the work of Lagrange, this hyperparameter is the force we apply to the beta parameters such that the sum over their squares remains a constant. This means we are forcing the parameters to move on the surface of a sphere in the parameter space. Therefore, we are minimizing the residual sum of squares under a constraint, a penalty of the following form. In machine learning, when the penalty term has a squared form, like in this term, the model is called the ridge regression. In this case, we usually say the regularization is given by the L2 norm. Let me remind you that this form of the penalty term is a direct consequence of the Gaussian distribution that we assumed for the beta parameters. If instead of a Gaussian distribution we had assumed a Laplace distribution for beta parameters, we would end up minimizing the RSS under the following constraint, where the regularization is given by the L1 norm. This model in machine learning is called the Lasso Regression. In this case, the hyperparameter lambda would represent the force we apply to the beta parameters to remain on the surface of a plane instead of a sphere. Anyways, one of the consequences of minimizing RSS under a constraint is that we end up with a simpler model, in the sense that it becomes equivalent to having fewer unknown parameters in the model. Therefore, adding a penalty term is a common solution to prevent overfitting. Now is the time to discuss the estimation of hyperparameter lambda using data. Remember that at the beginning of the video, I multiplied our previous probability distribution of rows of the spreadsheet by the probability distribution of beta parameters. By this multiplication, we made an assumption that we need to respect at this time. Just like the dice and coin example, where their outcomes are independent of each other, and that independence allowed us to multiply their probabilities. By multiplying the probability of the spreadsheet columns and the probability of the beta parameters, we have assumed that they are independent of each other. To respect that independence, we cannot use the same dataset to estimate the beta parameters and also the lambda hyperparameter. One common solution to preserve this independence while estimating both the beta parameters and the lambda hyperparameter is grid search cross-validation. Let me explain how this works. Let's say I have a data spreadsheet. Since the rows are supposed to be independent and their order should not matter, I will first shuffle the rows. Then, I will take the first 80% of rows as training set and keep the remaining 20% as the test set. This 20% will remain blind until I am done estimating both the beta parameters and the hyperparameter. Now I'm going to use the remaining 80% of rows to estimate the beta parameters and also the hyperparameter. However, since I cannot use the same rows for estimating the two types of parameters, because of the independence that we assumed at the beginning of this video, I will split this 80% of rows into another two separate sets. From now on, I will refer to the first set as the training set and the second set as the cross-validation set and the remaining 20% of rows as the test set. Now, I will assume a list of possible values for the lambda hyperparameter. I keep them between 0 and 1, for example. Depending on how much compute power I have, I can add between a few to a couple of hundreds of sorted values in the assumed range of 0 and 1. I refer to this list as the grid of hyperparameter lambda. Now I start from the first value in the grid, which means I assume that value for the lambda, and use the training set to estimate the beta values and the cross-validation set for evaluating the prediction power of that model. I will then repeat the same procedure for all the hyperparameter values in the grid and take note of the cross-validation scores for all of them. The hyperparameter value that returns the best score would be my estimation of the hyperparameter value. Let me also add another concept called k-fold. I can in principle perform the split of the 80% of rows into train and cross-validation set multiple times. That means after evaluating the score on cross-validation set, we shuffle the 80% of rows and split them again into train and cross-validation sets and re-evaluate the scores. If we do this k times, which is usually 3 to 5 times, we refer to this as k-fold cross-validation. The final score that we assign to the selected lambda hyperparameter would be the average of these k scores. At this point, both the lambda hyperparameter and beta parameters are set by the 80% of rows. Now I can use the remaining 20% of rows in the original dataset, the test set, to evaluate the final model on never seen data. Let me now switch the gear and discuss the bias variance trade-off. Remember that in our grid search for optimal lambda hyperparameter, I said we use a score to evaluate the performance of selected lambda values. One such a score that we can use for evaluating and selecting lambda hyperparameters is called mean square error, or MSE. As its name suggests, it is equal to the mean of the square of the difference between the target variable y and our linear regression model. Here the mean is on y, assuming the parameters are estimated and the x variables are given using the data spreadsheet. Let's now expand the square into the following form. Add and subtract the following terms, and finally rearrange the MSE into the sum of the following two terms. Here the first term is the variance of y, and the second term is the square of the bias in our model. If you have watched my previous videos, I discussed that in linear regression, the mean of y is equal to this term. That means in unconstrained linear regression, the bias is 0. But when we added probability distribution for beta parameters, which later turned out to be equivalent to forcing the beta parameters to remain on the surface of a sphere in ridge regression, or forcing them to remain on the surface of a plane in lasso regression, we are not allowing betas to take the set of values that make the bias term go away. That means we are increasing the MSE error by adding a bias. But instead, we now have the hyperparameter that we can adjust such that the variance goes down. That means we are trading bias with variance. Since it is the total sum of the variance and the square of bias that matters, it would be advantageous if we could tune the hyperparameter lambda such that the variance is reduced more than the bias increases, such that we end up with lower MSE at the end. Now, what does the variance of y mean? It refers to the amount of uncertainty on y values that our model predicts. Perhaps you have seen these error bars on predictions. These are usually the root square of the variance on y as a measure of uncertainty on our prediction. Therefore, By constraining the beta parameters, the linear regression line makes a slightly larger distance from the two y values due to the increased bias, but the error bars on the y will be smaller. That in turn means we are preventing overfitting, and our model has more prediction power, meaning that it can predict unseen data with lower uncertainty. Now is the time to see how to perform all of what I explained with a few lines of code in Python. First, let me import some Python libraries. NumPy is for holding numeric values in my spreadsheet when I perform the computations. Pandas is to read the spreadsheet from the file and pass the numbers to the NumPy containers. Next, I import two libraries for splitting the rows of the spreadsheet and the other to perform the cross-validation grid search. Next, I import both the rich and lasso regression models to be trained by data. And this line imports pyplot for plotting the curves. Next, I'm going to generate a synthetic dataset to use in the rest of the code. If you have your own dataset, you can skip this block. In this block, I'm assuming 400 rows and 9 columns in the spreadsheet. This line generates the random data for the predictor column and features of the models. In this line, I'm generating the y column data using this formula. Here, I arbitrarily selected these coefficients for the regression model so that I can compare them with estimated ones at the end of the code. I also added a bit of noise to the y values so that it won't be a perfect line, kind of making it similar to real data. Then I create the pandas data frame, add the x and y columns to it, and save it in case I want to use the dataset somewhere else. And here is the generated spreadsheet with the last column being the target variable and the rest of the columns being the predictors. In this column, I read the data from the file and store it in a data frame. In the case of real data, this line would be my first step. Next, I created the features matrix, the spreadsheet without the y column. And here is the y column of the spreadsheet. In this line, I split the dataset into 80% and 20%. This function automatically performs the shuffling of rows before splitting them. Here I define a dictionary to hold all my hyperparameters. In this video, I only have one hyperparameter, and so far I have been calling it lambda. But in this Python library, they named it alpha, just different naming. Note that the dictionary key name is not arbitrary, since the grid search function below will internally look for a key name called alpha. And here are the values in my hyperparameter grid. Next, I initiate the model to be the rich regression. I can also commit this line and uncomment the second line to instead work with the lasso regression. Note that at this point, the model is not trained yet. That means the beta parameters are not known. Next, I perform the grid search. The first argument is the regression model. The second is the grid of the hyperparameter. This number is in the k-fold that we discussed in the video. For scoring, I'm using R2 instead of MSE since that performs better in hyperparameter tuning. Although MSE is also implemented in the package, and for using that, I need to change the scoring to this value. Number of jobs refer to the number of cores I'm going to use. -1 means all of the cores that are available in my computer can be used. And the next line performs the estimation of beta parameters as well as the hyperparameter. In this block, I plotted the score on the y-axis and the grid values of the hyperparameter on the x-axis. Unlike MSE, in the R2 score, 1 is the best score. In this plot, note that the score is the highest when the lambda hyperparameter is around 0.2. Note that lambda equal to 0 is the unconstrained linear regression. Here I'm printing the best value for the lambda, in this case alpha, hyperparameter, and the R2 score for the cross-validation, which turned out to be quite high. In this line, I set the hyperparameter to its best value to create the final model, and then test it using the 20% never seen data. As you can see, the R2 score is still very high. And finally, here are the estimated beta coefficients of the best model and the values that I originally assumed to generate the data. You can see that the estimated ones are very close to the true values. Finally, to get the human-written source code that I just presented, you can log into our website at www.compu-flair.com and use the search engine to find the corresponding pipeline. Next, select the pipeline using the drop-down menu. The source code that it will return is human-written and free of AI mistakes. Also, if you have questions regarding the code, or if you need assistance modifying it, ask the chatbot and it is supposed to help you with that. We have added some hidden prompts and instructions to make the chatbot less prone to common AI hallucinations. I hope you have enjoyed this video. Take care, and I'll see you in the next video.